In this video, we now want to see how to use the kinematic equations we had from the last video through the use of some examples. So let's look at this first example here. We have an airplane and it's starting from rest and it's accelerating down the runway at 3 meters per second squared, and it needs to achieve a final velocity of 33 meters per second before it can take off. I want to know what is the minimum distance delta x that the runway needs to be for the plane to be able to take off under these conditions. Now, notice time does not appear anywhere in this equation or in the given information. So I need an equation that does not have time in it. And fortunately, we have such an equation in this. And this equation is one of the kinematic equations we saw from the last video, and notice that it does not have time at all anywhere in the variables. And on top of that, it relates all of the variables that I'm given to what I'm trying to find. I'm given a VF, I'm given a VI, I'm given an acceleration, and I want to find delta x. So my task now is to solve this equation for delta x and then plug in the numbers and see what pops out. So, first things first, I notice that VI is 0, so I can eliminate that term right away. And this reduces then to VF squared is equal to 2a delta x. And that means that delta x is going to be equal to VF squared over 2a. And at this point, you can plug things into your calculator. And if I square 33 meters per second and divided by 2 times 3 meters per second squared, my final result should be 181.5 meters. Okay, so the runway needs to be a minimum of 181.5 meters. If the runway is any shorter than that, the plane will not be able to achieve this velocity with this acceleration. All right. Now, technically, according to sig figs, this should be 182, and in fact, technically, according to sig figs, it should really be 180 because I only have 2 sig figs here. But anyway, you get the idea, okay? That is how I can apply this equation to this particular situation. Now let's look at this situation over here. We have a high cliff, and we're dropping a rock off of the cliff, and we note that it takes 3.25 seconds for the rock to fall and hit the ground. And I want to know what the height, delta y, of the cliff is. Okay? So I want to know what the height of the cliff is. Now, we are going to assume that we drop the rock from rest. Okay? So I'm given that I drop my rock from rest. The time interval is 3.25 seconds. I'm given the acceleration of gravity, the acceleration that the rock experiences, the acceleration due to gravity. That's 9.8 meters per second squared. We haven't really gone over that yet, but we're going to use that quite a bit in the coming chapters. So we're kind of jumping the gun here. But anyway, so I need an equation that relates displacement, the displacement of the rock from the cliff down to the bottom, acceleration, time, and initial velocity. And indeed, I have such an equation. And in the previous video, we had delta x here, but remember that delta x is just a displacement. And now because we're in the vertical direction, we are dropping things and letting them fall or launch upward or downward, we just substitute delta y for motion in the upward direction or downward direction versus delta x in the horizontal dimension. So this equation is exactly the same in spirit as the delta x equals VIT plus 1/2 AT squared. The physics is exactly the same. So I can use this equation, and notice again it relates all of the variables that I have. I'm given an initial velocity, I'm given a time, and I'm given an acceleration, and from that I want to find the displacement of the object. So now all I have to do is, actually I don't even have to solve this equation, it's already solved for us. Now it's literally just plugging in the information. If I were given the displacement and I wanted to find the acceleration, for example, I would then have to rearrange the equation for A, do some algebra, and then I can plug in. But as it stands, all I have to do is plug in my information. So Again, VI being 0, I can get rid of this term right here. 0 times anything, even though the time is 3.25 seconds, 0 times anything is 0, so this initial term disappears. And therefore, I'm going to be left with 1/2 AT squared. Now, when we get to free fall, we will actually put in g here. We will write the symbol lowercase g, and that means the acceleration of gravity. This is the special symbol that we use exclusively for the acceleration due to gravity. But if I now plug in my information, okay, notice that my 3.25 seconds squared, I have to square this, and now if I square this, multiply it by 9.8, which is really close to 10, and then cut it in half, the result is about 51.7 meters. Actually, it's very close. We round up to 51.8 because it's 51.75 and some string of decimals. So we round that up to 58. But again, if I'm going to be technically correct with my significant figures, I have to round, because I only have 2 sig figures here, I have to round this to 2 significant figures. So this is going to be 52 meters, all right? Now, let's look at one final example where we actually have to do multiple steps to find our final answer, okay? If you have any questions over these, feel free to watch these videos over and over and over again. If you still are having issues solving these problems, feel free to email me and I'll help you out. But now let's look at an example. That's similar to these, but slightly more complicated. So, let's say we have a car, and I'm a horrible artist, no making fun of my artwork here. So we have a car, and it's moving along with an initial velocity of 21 meters per second, and then it starts to apply the brakes. So it's going to slow down. So even though its velocity is in this direction, okay, it's going to slow down in this direction, and it's going to have a final velocity after it applies the brakes of 0, right? So its velocity is moving forward. The acceleration is in the negative direction, and that means that it's slowing down, and then it comes to a stop. And it does so in a time interval. It applies the brakes for a total time of 6 seconds. And the question is, what is the displacement? How far did the car go from the point of applying the brakes to completely stopping? What was that total displacement the car experienced? Now, we are not given the acceleration. So this is an example where we actually have to solve 2 separate problems at the same time. And we are given initial velocity, final velocity, and time, but we're not given acceleration or the displacement. So we have 2 unknowns, therefore we need 2 equations. So how do we go about this? Well, to find delta x, both of the equations that involve delta x equals VIT plus 1/2 AT squared, or VF squared equals VI squared plus 2A delta x, both of those involve the acceleration. So I need to find the acceleration before I can find the displacement. And fortunately, I'm given VI, VF, and delta t, so if I go to the definition of acceleration, the definition of acceleration is just VF minus VI over delta t. And so I can find my acceleration this way, and this is going to be VF is 0 minus 21.0 meters per second. And if I divide that by 6 seconds, my acceleration is going to be negative 3.5 meters per second squared. And now that I have this, now that I have my acceleration, I can actually calculate what my displacement is. I can actually calculate it by either method, okay, by either method. If I calculate it with the first equation, VIT plus 1/2 AT squared, do note a couple of things, okay? First things first, my VI is positive, so this is going to stay the same, but my acceleration is negative. So what I can do is go ahead and put a negative sign out front here. Okay? So I can now plug my numbers into this equation. Or I can even plug them in to this equation. And again, I can note that my acceleration is negative. And then I can solve this equation for delta x. But I note, one thing I can do is note that my final velocity is 0, so this term goes away. And now if I solve for delta x, I can do as I've done before, but this time I move the negative 2a delta x, I add 2a delta x to both sides, and I'm going to get the final result. I'll just write it down. The final result is delta x equals vi squared divided by 2a, and my a here is going to be positive because I've already taken the negative sign into account right here. And note what happens in both cases. This term is going to be larger than this term if you plug it into your calculator, and this term is also positive. So my displacement should be positive because I'm considering the origin of my coordinate system implicitly starting from here, so I'm moving in a positive direction, and so my displacement should be positive even though my acceleration is negative. So I do want you guys to be aware of that. This is where the vector nature of the acceleration and velocities is starting to come into play, okay? But my displacement should be positive because I'm moving in the same direction that my velocity is moving, and therefore my overall displacement should be positive, and it's going to be positive because 21 times 6 is larger than 3.5 times 6 squared, and then cut that in half. So if either way I do it, my displacement is going to be positive. And I'll leave it to you. You can actually show that both of these numbers give you the same answer. And that allows you to convince yourself that these equations are consistent. Okay, so that's how we solve examples with the kinematic equations. And in this example, we actually had to use 2 equations since we had 2 unknowns. Hope that helps, and happy problem solving.